Hi, welcome to this lecture on data structures. Today, I'm going to cover the topic of implementation of queues using linked lists in C. To give a quick recap, we will try to define the definition of queue as an abstract data type. So queue is defined as a collection which has a constraint of first in, first out, also abbreviated as FIFO. The elements in the collection of a queue can belong to any type, T, which can be simple or primitive types. It can be a complex type like array or a struct in C, or it can be another abstract data type with its own set of model and operations. So this is the definition of queue as an abstract data type. It doesn't talk about implementation details. It doesn't talk about the structure of the data. It just gives the specification of the model along with a set of operations. And the operations defined for a queue are insert, which puts in elements into the collection, and delete, which removes elements from the collection. Insert is also called as NQ, and delete is also called as DQ. And we might also have functions like size to get this count of the number of elements in the queue. Moving on, we also learned about the linked list data structure in C. To give a quick recap, linked list is also a collection of non-contiguous data items. Each element in the linked list takes a form of a tuple where the first part will hold the data of the element, and the second part contains the link to the next node. So this specialized structure is called as node, and this can go arbitrarily long till the last node, which doesn't point to any other node. We have implemented this in our previous lectures. We have a head which points to the first node, and we have a list which has the head as one of the data members along with the size of the list for convenience. One advantage of linked list is that it can support arbitrarily long collections. The size of the linked list is not limited either at compile time or runtime. It can dynamically increase depending on the requirements. So now let us see how we can manifest the queue abstract data type using a linked list. The mathematical model of the queue abstract data type, which is nothing but a collection, can be mapped to linked list easily because linked list is also defined as a collection. But how do you model the constraint of FIFO using linked list? This is where we would like to use the list abstract data type implementation using linked list. To elaborate further, we have a List ADT that also is an ordered collection of data of type T, which can be a simple complex ADT in itself. And the ordering of elements present in the list owes to the fact that each element in the list is mapped to an ordinal, or it's also called as an index. And this ordinal or index can be used to order all the elements. And we can mimic the FIFO behavior of a queue by ordering the elements in the list in such a way that when delete or DQ is performed at an index, that index has the least recently inserted element. So to elaborate further, we can map the operations defined in queue to the operations defined in list in such a way that when queue's delete operation is performed, the list's delete operation is performed at an index where it is guaranteed that the least recently inserted element exists. So to achieve that, what we're going to do is to map the insert operation of a queue to the list abstract data type's insert operation at the index 0. And we map the delete operation of a queue to the delete operation of the list abstract data type. If you consider this as your linked list, so you have a head which is part of your list structure, which eventually points to your linked list. So when insert of element is called, the insertions happen at the 0th index. So this is where the inserts happen. And we have seen how inserts are implemented in linked list for the list abstract data type implementation in the previous video. So this is where the inserts happen. And the most recently inserted element in the linked list is present at index 0 for a linked list, and indexes in linked list are nothing but the distance of the node from the head of the linked list. So the index of the most recently inserted element into the linked list is 0, and the next most recently inserted is 1, 2, 3, and so on, and the least recently inserted element has an index of the size of the list minus 1, which is, in this case, you have 5 elements and the size of list minus 1 is 4. So 4 is the index of the node which has been inserted least recently. It is the node that has been inserted before any other nodes in the linked list, and this is the one that is deleted when you call delete for the queue. So you delete the node at size of list minus 1, which is this. This is the most old node in the structure. So this is how we try to implement the queue using the ordering of the linked list, and by making sure that we only call the list API operations defined by the list abstract data type, we make sure that we are not dependent on a particular implementation of the list abstract data type. If the list abstract data type implementation changes, we can simply point to the new implementation and keep our queue implementation code independent of the list implementation code. And this is the exact same implementation that we had for the queue implementation using arrays. This is the exact implementation that we had for the queue implementation using array. Nothing has changed in it. The implementation remains exactly the same, except that in the background we used a linked list implementation instead of an array implementation of list. So this is the implementation for the queue, which has the following methods: queue insert, queue delete, and isEmpty. I mean, these functions can be called as enqueue and dequeue, more standard naming convention. And the linked list has the following functions, which is the standard list abstract data type definitions. So you have size, first, last, inserts an element at a given index, deletes an element from an index, get index is something that returns the index given the element, get returns the element given an index, append basically puts the element at the end of the list. The data structure for the linked list is the same. The node has a value and a pointer to the next node. We additionally defined an element called tail, which I'll be talking about in a little bit for efficiency reasons for implementing the queue, but otherwise we have a head and the size, which is used to keep track of the number of elements in the list instead of having to traverse the entire linked list from the head to the last node. And this is a sample implementation of the list backed by a linked list. Most of it is the same as what we had discussed in our previous lecture, except that I've added a new pointer to point to the last element of the linked list to optimize the deletion of node at the end of the list. We'll be talking about optimizations of the implementations that we saw so far for stacks and queues using arrays and linked list. Try to analyze the runtimes and see how we can optimize them in the next lecture. But this implementation is the same as we did for the list in our previous lectures, except for the fact that we have added the tail pointer. And the most important point is that we have not changed anything in the implementation of the queue. It just calls the insert method of the list abstract data type. So this is 0 and this is so these are the actual methods. So we have inserted we inserted the 0th index, any new element into the queue, which means that all the elements progressively are older than the previous one. So the oldest element which has been inserted into the queue will be at the end, which is size q minus 1, which is from where we delete to ensure the FIFO structure. Let's try to run this code and see how it behaves. So what we're trying to do in the driver of the program is to insert 1, 2, 3 and delete a couple of them, check for the emptiness, delete the last one, and then again check for the emptiness. So you see 1 is inserted at the 0th index, 2 is inserted at 0th index, 3 is inserted at 0th index. When we remove it from the end. So 1 was the first element that was inserted into the queue. That's the one that should go according to the FIFO logic. And you have 3, 2 remaining. We do a delete again, which would push out 2 out of the stack. And we are remaining with 3. isEmpty will return 0. When we do a delete again, 3 will be removed and isEmpty now returns 1. So That's the end of this lecture. We will meet in the next lecture where we are going to discuss about various implementation strategies that we have for list and stack in terms of arrays and linked list, and try to analyze the performance of each of those strategies, and also try to arrive at the best possible implementation in terms of the efficiency of our code. To also add, we might not have implemented the most efficient solutions for our data structures for both queue and stack. We might not have done that because we were focusing more on designing the programs, getting the functionality right. Premature optimization is something that is probably not a good idea. Optimization is something that you have to think about when your design is mature. It's at a stage where you are comfortable with your functionality being implemented, and that's when you have to then look at your optimization problem. So that's what we'll do in the next lecture.